We'll need a drive today. Yeah, give it a second. It's gonna.
Oh.
Okay, so today we're gonna talk about TCP IP model or 3. Let's see if I have to turn off the setup screen. All the remote. Okay. So we're gonna proceed with chapter 5, and then we're gonna look over our lab. So today we're gonna work with our server machine, our server virtual machine, and we're gonna work with DHCP today. Okay. And then in the next few weeks, we're gonna start working with routers and switches. So we'll start with packet tracer first, and then we'll move into actual routers and switches. So in at the beginning of chapter 5, it goes over your TCP IP model, which is very close to what you've seen with the OSI model. Now, the difference between the OSI model and the TCP model is that they condense it into less layers. So instead of 7 layers in the OSI, which we've talked about before, most of the TCP model, sometimes you do see them as just 3 layers, but the standard one that you see is the 4-layer TCP IP model. So this is what it looks like. So the top 3 layers of the OSI is condensed into one application layer. Transport is still equivalent to the transport layer on the OSI. Same thing with network. And then your data link physical is condensed into network interface layer. For Network Plus and CCNA, make sure that you know the TCP IP model and you understand the differences in these models. On the image, it also gives you some of the common security protocols that each of the layer. So for example, SSH, PGP, this is pretty good privacy. It's used for email encryption. SSH is when we directly connect to a system, like if I am connecting my computer to a Raspberry Pi or a router or a switch, or a server, you can use PKI to connect with encryption with secure shell. SSL TLS, that's when we see with HTTPS, and we normally use this for secure session. So it breaks down to some of the some of the protocol that you see. And then point to point, this used to be on how we would connect for remote access, but we no longer use that. We use newer technology, but it does give you the breakdown for that. So for interviews and exam and quiz for this class and also certification, make sure you remember the protocols in the layers for TCP IP and the OSI. Okay. All right, let's go through and answer some of the questions. So the first question asks you, identify the TCP IP model layers and describe their functionality. So we mentioned that there are 4 layers. We'll start with the first layer, which is your network interface. This layer is responsible for physical connection, the same thing that you would see with the physical layer in OSI. It is physically connecting the device or linking signal in the devices. So compared to the OSI network interface, combines the physical and the data link layer. So this is when you see cable is generating signal, and that signal is passed, right, into the computing system or into the network interface card and be able to generate communication at the lower layer. We'll need a drive today, okay? On the next layer, which is often referred as network or internet, in the book that we are using, it says network, but sometimes you see is that network/internet. This is responsible for information delivery after the connection is established. So it needs the network interface in order to establish the communication. Then the network internet, which is the next layer in the TCP IP model, is responsible for delivering information. And this is equivalent to your network layer in OSI. This is when routing takes place. And then you have the transport layer, which is following the networking internet. This is responsible for connection-oriented communication. And I think we previously established the understanding between connection and connectionless. So connection-oriented, it requires an established session. Connectionless communication, it does not require a session. So transport can happen in both ways. Connection-oriented transport or connectionless transport. One, which is connection-oriented, required a session that must be established, where it has the acknowledgement in the communication. And then connection-less oriented, you often see this with UDP, right? That doesn't require the session. Any question? So make sure we know the functionality for each of the layer. And then lastly, your application layer, which encompasses the top 3 layer in OSI. Application is responsible for making network requests from the source, which is your sending computer would send the request, or servicing the request, like the server providing the response back for the receiving computer. So this is a 4-layer TCP IP model. Traditionally, you do see some 3-layer model floating around, right? But I think now the industry mostly follow the 4. As long as you understand that when you troubleshoot, you would start with the network interface, going into the network and internet, then we'll move into transport application, and then it cycles through again. So these models are really built to help you understand how to look at communication when it's established, and then be able to use each layer for troubleshooting. So when we look through our notes, we would see some protocols. Let me move this up a tiny bit so you can see the top. So we need to identify 2 to 3 protocols for each of the layer in TCP IP model. So when we're looking at network interface compared to OSI, that's the first 2-layer, physical and data link. We would see Ethernet, which is standard 802.3. This is what you see with the cable Ethernet that you had created in the prior lab. Or you would see wireless, like Wi-Fi, 802.11. So it can establish communication via airwaves, which is in Wi-Fi, or would signal across your copper twisted pair, which is the Ethernet. Then when we move into the next layer, which is the network of internet, this is equivalent to OSI network, so we can say IP, and we talked about how IP is purely for addressing. ICMP, that's for pinging, right? You got ARP, address resolution protocol, and then IGMP. So these are some of the protocols that exist or operate in the network internet layer, which is equivalent to network and OSI. And then transport, you got connection oriented, which is TCP, right? TCP. And under the umbrella of TCP, you see like HTTP or HTTPS. And when we did the Wireshark lab, you saw that when you have HTTP requests, you do see some acknowledgement in the conversation. So in order to establish the communication, it needs to make sure that it is connected and it acknowledges the connection. So that's TCP. That's more reliable, but it is slower. Where user datagram protocol, your UDP, it doesn't require the acknowledgement. And then at the application layer for HTTP and HTTPS, that is because through the browser. So when you think about application, you can say what kind of application opens up my website, and my website uses HTTP and HTTPS. Telnet, we don't really use Telnet because of the lack of security these days, right? But Telnet is a way that we can directly connect with the system, and you can see everything in plain text. So we normally turn Telnet off. The same thing with Secure Shell is a direct connection to the device. For example, I use my laptop and I need to configure the router. I can use SSH, which is preferred and recommended, but I can also use Telnet. We normally disable Telnet for security reasons, and we would revert to SSH. This is a way that we can directly connect to the system. And then your NTP, that is for synchronizing the time. So network time protocol, that allows your server to synchronize time across the network. For example, when we do daylight saving, that's part of the service that you see. So as long as you're connected to that particular network, your device gets synced with that clock. We do this for replications, batch processing, on the back end, it's a little bit different because sometimes you only have a small gap in how the time is different across in the servers in order for it to synchronize the data. So NTP is very important, but on the back end, we also see NTP also has flaws, right? Somebody can capitalize on that to do denial of service or distributed denial of service. So these are some of the protocols that you can identify in each of the layer. Any question? And you can see that on the picture, the images, right? And it gives you the description for each of the layers, starting from the top, which is the application. So you see web server exists there. And then NTP. So when they refer to PDC, right, that's primary domain controller. So if I install a DNS and I promote it in the domain, it becomes the primary domain controller. In the past, the reason why we name it this way is because in order to synchronize across, you have to set a primary and a secondary. So you do see like, the main server, and then we can sync that down to some of the the smaller, the sub-server. We don't really refer to it like that anymore. We just refer to parent and child, but this is because it's from the Windows NT days. And then in the back, you still see some of the legacy terminology and how the system identify itself or to others. And then there are additional protocol that's listed in some of the layer here. Hello. You need a drive for a lab today, so make sure you pick one up. Okay. So in the past, we also talked about network protocol, so you can refer to Unit 2 notes for additional information on the protocol. So let's talk about flags. And we saw these flags when we run Wireshark, or when you run network monitoring, when you're looking at specific packets, especially TCP packets, you often see the flag ACK. That will be acknowledgement for the packet, whether it's received or not, right? Or sometimes you would see fin, FIN, that's for a finish flag or final, right? And then you also see other flags here. And then sometimes you see SYN for synchronization. This is where the packets would then be able to establish or be able to send with the three-way handshake. So there gotta be a synchronization. So how does the system know when it's ready? It uses these flags to determine the state. So in the next question, it asks you to provide the flags, and you can simply grab that from the notes, or if you wish to type it, you can. So SYN, it's assigned to any packets that is part of the SYN phase. So it needs the SYN, the synchronization of the three-way handshake. And we talked about that. That's for acknowledgement that the previous packet has been. And this is important because otherwise you're gonna have loss in packets. As we know that we have collision in the network, we would have systems sending simultaneously across multiple systems, might be communicating at the same time. So how does it know whether the packet gets to the destination or not is through these flags. So there gotta be a way that it notifies, other system that the packet has been received. It's kind of like how when you receive a package and you sign for it, right? ACK is like that, your signature that you have received that package in the mail. And then you have push flag. This is a way that we can force data onto an application. So you do see some system that might use a PSH or a push flag. This is a way that we can force data. And then the priority, how does it know which packet to get to first? So it's like how you ship or you send your mail, right? I can put it into a priority envelope and I can send it, and that gets sent first, right? It gets delivered to the destination first, but you gotta pay more. So there is URG, that flag is gonna tell the system that that's an urgent, that it's gonna take priority when it sees this flag. And then you have a reset, which is RST. So at the end of the conversation, it has to do an RST, so that way it flushes out that conversation and it would then communicate. It's establish a new conversation with the other system. So when you do the follow conversation in Wireshark, sometimes you would see an RST at the end of the conversation. So this is going to help you understand a little bit more when you're looking at the Wireshark packets, We've seen some of that. I had you take a look at it, follow the conversation, looking at the statistic. But the more you dive deeper and you're looking at the headers and you're looking at some information for each of the packet, you can further understand, what these flags would do, what kind of packet that is, Does it have priority or not? So all protocols have some form of headers. Think of it as a way for the system to simply see some kind of main information that it needs to send and receive. TCP has some form of headers. UDP has some headers. So when you're looking at the packet and you look at source, destination, right, timestamp, that's all part of the header. And UDP, unlike TCP, the headers is a little bit less complex. Okay. So in the header for UDP, it would include these things. Source port, where that's coming from, right? So the source port is different than a source IP address. As you know that when it sends, it needs to either have a logical port or a physical port or sometimes both. So a source port is a communication point that the system is using to send from. So it's dedicating 16-bit, which is 2 bytes from this port, right, by sending the application on the sending system. So when I'm looking at DNS traffic, right, like port 53, DNS uses UDP. So on port 43, right, it's gonna be able to tag that port as a source port, port 43. So when you're looking at that packet, it's gonna show the source port where that's coming from. And then you have the destination port. It's also 2 bytes. Okay. And it uses the 16-bit field to indicate the port for the application to be received, right? That's the receiving end, the destination. So in the header, you often see that where it's coming from, where it's going to. Source and destination, right? UDP in particular, it uses the port. And then you also have 2-byte field or 16-bit field that would specify the size of the headers in bytes. It's going to say, oh, the entire header is going to be this big. And then it does a checksum. This is it's used to verify the integrity of the UDP header. Now, compared to TCP, it lacks the sequence value because TCP would require things that gets back into the entirety in order to open. For example, right, I'm going to go back to my analogy for a bicycle. For TCP, it's going to wait for the whole entire bicycle to be assembled. Handlebar, right, pedals, wheels, brakes, all of that in order for it to present that it is a bicycle to the user or to the application. UDP doesn't do that. UDP just present, oh, here's the wheel, here's the brake, here's the pedal, here's the handlebar, right? It doesn't have a sequence value to really indicate, yes.
UDP is really good for like streaming, like watching like videos and stuff like
Right.
that.
Yeah, and it opens as it arrives. So it doesn't care whether, 1 through 10 has already been. So on TCP, it's going to require that it's going to be from all the packets is going to be in the proper sequence in order for it to present. So there's a validation for TCP acknowledgement, right? And when it gets to the finish is going to say, oh, okay, that's the last packet in the conversation. Now it has the entirety of what the payload needs to be, and that's how it presents. So compared to TCP header, your UDP header has less fields, right? It has where it's coming from, where it's going to, the size, and it does do the checksum. That's just for integrity purposes, right? We want to have validity, even though it opens as it arrives. Okay, so you can take a look at how the layout for TCP. So it does have the same, you see, source port, destination port, but it has the sequence number that I referred to right here. It also have acknowledgement number, and that's important for TCP because that it's a three-way handshake. It's gonna ask, hey, are you ready to send? And then the other one says, oh, okay, I'm ready to send. Okay, let's send. And then once it's sent, okay, I received, right? So you got communication back and forth, and so therefore additional fields is there. And then you got these flags that we talked about. Okay. It does also have the checksum as UDP, and then there's priority. So this pointer just point back to the flag, and that's how it's able to determine there's priority. And then your payload is down here. It does tell you the size of the payload, your data. Okay. And then there's additional things like offset, reserved, window size. So when you look at the TCP packet, you have additional information compared to the UDP header. So if you need the reference for the notes, you can go to page 4. So it's a little bit less in the header, right? There's only a few things, which is nice. Now, in the network layer, we talked about how IP, ICMP, ARP, IGMP exists there. That's used there. So for the IP header, here's its content. Everything is 32-bit, right? We mentioned that as we represent this in what? Our IP addresses as well. Okay? So it has these fields, and that's how it used. But ultimately, it uses address because remember that this is a network layer. So compared to the other layer, right? This operates in the network layer, so it needs the addresses. You got the source, the destination, and then you have the TTL, time to live. Otherwise, it's just going to keep going, and you don't want a system to hog the bandwidth like that, right? So they design it to be, it's going to time out at a certain point. So it's going to go back into queue and then try to resend. Okay, so here are the fields. So let me put the answer up since. So the IP header, what fields specify when the packet expires? It's your time to live. And so when you're looking at the TTL, it's going to give you a value, and that value really indicates how long, right, that packet is going to send for. And if it times out after it expires, right, that's the value that's going to go by. I need a drive for our lab today, so make sure you get it. Okay, so I give you each field information, right? There's versions. Why is this important? This indicates version 4, version 6. There are 2 types of addresses. You also have the header length, the type of service that's used, that's going to take up a byte. And then it needs to also check the length of the IP packet, which is 16-bit. It has the identification. This is for your MTU, maximum transmission unit. This is going to allow you to break the data into fragments. Remember that your data doesn't get sent as a big old chunk. It actually chunked it up to many packets. And so it uses the identification to really seize, like, right, which packets for which data. And then you have the flags. And then the fragment offsets. That requires 13-bit. Time to live is about a byte. And this is important to kind of look at decrement in every router and the packets pass through. So every hop that it gets sent to, right, it's going to do a decrease because whether the hop is farther or closer. So as it approach closer to the destination, it's going to do a decrease. It's going to subtract 1. And then that's how it's going to be able to get to the destination. So let's say that I'm 10 hop away, right? And it's going to go 9, 8, 7, 6. And then when it gets closer to the destination, the router to router is going to say, okay, I'm only 1 hop away. So when it gets to the destination, it becomes 0. That's how it's able to know that it reached the destination, right? And then also the router also does the calculation on the distance as well. Then you have protocol, header checksum, destination address, 32-bit for the source, 32-bit for the destination. Okay, any questions regarding IP header? Okay, make sure we read through. It's important to remember these things for certifications. ICMP, Internet Control Message Protocol. You saw this with ping, right? It's included with that service. This allows the system to share status and error information. So if I don't have a reply, right, it's going to tell me that it's timing out. So in the next question, question 6 asks you, what is used by
Can you break it down a little bit?
what is used by ICMP to identify different types of messages? So it uses codes and type to be able to differentiate the messages. Codes and types. Now, when we're looking at ping in Windows, generally it's going to send 4 packets from the source to the destination, right? And then it's going to give you the status, whether there's response for each of the packets or not, right? And then the statistic. If you're doing it on Linux or other type of systems, you would see that it continues unless we specify the count. So that's often that you see ping with ICMP. And then you can do trace route, right? Don't say trace cert. It's trace route. In Linux, you have to spell out trace route, and in Windows, it's trace RT. So what we can do is we can trace, right? Let me see if I can do that here. Now, sometime when you do a public IP, you don't always get a response. So if I do trace RT, now in Windows, it's only going to show you 30 hops at the max, but normally the display is like a few less than 10. So what am I following? I am actually tracing my traffic from my computer to Google server. This is one of the address that's owned by Google. So here I am, right? Leaving or from the RCCD network, right? There's connecting back to the wireless side. This is exiting RCCD network. So as you know that this is actually a lot longer than we're actually just visiting the Google server website, right? Or the Google website, because it needs to report back as it's crossing over to each of the gateway. So now I'm getting to the internet service provider, right? And then I get to the destination. So my trace is complete. And so ICMP is used for trace route this way. And so you can trace inside your local area network, you can use a private IP. right? It will just trace from one system to the next, and you can do that for troubleshooting purposes, like if you have a local server. But over the networks or in the wide area network, you can trace with the public IP. Simply do trace RT and then the destination address. Okay. And so similarly, you do see that it does have a time to live. So when you see timeout, when the system is not response, it exceeds the time to live, right? That value is exceeded. So it's going to start at 1 and it's going to go up. So if you get the error when it times out, it's because it exceeds that time and the system doesn't respond. So when you're trying to trace like a Facebook, Instagram, social media server, if you can find their addresses, they are going to use a block. So you can deny ping or ICMP services. And normally that happens with the firewall. So they would prevent that service from the request from coming through. So it kicks it back and then eventually it will time out. So they do that because, attack you can do a Smurf attack where you can ping someone to death, right? That's very old school, but it's still being used. So ICMP is very popular in many ways, in troubleshooting and finding the state of the system, but also in attacks. Okay. So here it tells you the code, which is what we answer, right? And the code really indicate the status. The header looks similar to the others. You do have some components that are the same, but because it used the type, which is 8-bit, and then a code, which is a byte or 8-bit, that's how it's able to identify the status. So type and code indicates whether it's being used. Any question? Okay, we're gonna do conversion in a little bit. Okay. So the 3 types of addresses, oh, I'm sorry, I skipped number 7. Number 7, identify the type of IPv6 addresses. You have 3 categories. You got a unicast, a multicast, and an anycast. Unicast sent to one, multicast sent to a group, anycast sent to anybody or any system. Now, a little bit different than version 4, where we have unicast, multicast, and broadcast, right? Yeah, anycast is kind of like broadcast. It sends to any system that's listening. And so when you're looking at just unicast addresses, how does it break down? There are 3 types. One is a global unicast, which is your public address. That's equivalent to IPv4 public address. So when you see a global unicast on your report or when it's indicating global, that's a public IP. Then you have a site local unicast, that's a private address. That's used inside your local area network only. Right? That's the value that indicates the private. And then you got the link local unicast, which is for linking only. So if IP version 6 is not fully configured, you often see that it's going to show up link local unicast when you're looking up IP address. For example, if I go to my Kali Linux virtual machine, I think I had you guys do optional part B last week. Some of you let me know that you didn't, right when you submitted your assignment, I saw. But I didn't require that. But when you look up IP address, you would see that version 6 is there, but it's not fully configured, right? It's not in use. So it does show like the broadcast, which is all Fs, or the anycast, and then you see the link local unicast, and it will say link local. So when you're looking at IP version 6, it's slightly different than your version 4 in that it breaks down, of course it uses hexadecimal. That's different than the way its layout is different, the format is different, but we need to understand the category. So when we look at our IP configuration, we know what that is.
Also 128-bit.
Right, 128-bit, which gives you longer address length and also a lot more combinations. It's 2 to 128, right? But will the world run out of IP version 6? They're predicting that we will, and then we'll have another schematic for addresses. And that's probably beyond my time, right? So it took us what, about at least another 10 years after IP version 4 expired to kind of fully, I don't think we still even fully integrating, we're still using both, but we haven't transitioned completely to IP version 6. Some networks are, and most of the networks aren't, right? And that's 2011 was when we ran out of the version 4 public IP. And so, a lot of the tech companies, they hoard IP. And now I just read the other day that Microsoft is buying out, like, the nuclear plants that were shut down a long time ago. Now they're revamping that. And on one of the islands, and Microsoft basically bought them out because now power is control, right? So they're buying out all the power generating from that nuclear plant to be able to support their and others data center. Okay. So for reference for this, you can take a look, but I want to touch back on this so that way we know. So IGMP, Internet Group Management Protocol. This is for a multicast protocol for the suite. This is used to send to multiple systems at once. So if you are looking at multicast, like if I want to send to one segment, I can use IGMP to do that. We do that for, reasons like, waking the systems up, patching, imaging the system. So we might not want to image all our entire network, but let's say that I have a department that needs new software, new application, new OS upgrade. I can do that through IGMP, definitely, right? Beautiful. Address resolution protocol, ARP is important. I know some of you have taken 27 and security classes. We talked about ARP poisoning. ARP is a very important protocol because it broadcasts a message as a request to the destination. So it's going to wait for the reply from the physical address and the origination system. So the process with this is, with ARP, it's converting the IP address to MAC and MAC to IP. You need ARP to pinpoint the system, okay? ARP is going to narrow down which system that is in that segment because it's going to use the IP address and correlate that with the MAC address, okay? Now, how do I do ARP poisoning? Well, I can modify one of the two. Right? If I'm spoofing, if I'm pretending to be your computer, I would have to perform an ARP poisoning. I would have to modify your computer, right, with some sort of information, or my computer with your MAC address, right? I'm going to pretend to be you. So I'm going to have to make sure that the other systems see me as you, right? So ARP poisoning is just a way that we modify what the other systems see. And so that way we can tell the other system that we are the other computer. And so when you're doing IP and MAC spoofing, that has to deal with ARP, okay? Even if you use an application, that's what's happening in the back. Okay. Network access layer, network interface and link layer. So one of the things that you would also see with version 6, besides the address space and its functionality, and you can also use IPsec with it, right? It's built with the protocol suite, so that's definitely good for remote if you want to set up for remote communication. It does reduce with the overhead. But if you look at most of the network, right? If you don't believe me, you go, let's say that you come in as an intern, you troubleshoot. When you're looking up IP addresses, private IP is still being used with IPv4. Traditionally, because we do have a lot of legacy system that gives and sees only version 4. Okay. Okay. When you see a loopback address, it will be like this. Sometimes it condenses it, so it might be shortened. And then if you see a multicast address, it's going to start with FF01 prefix. Like this. So when you see a double colon, those are the bunch of zeros in between. Right? And then 1 or 2 at the end. And a lot, you know, the automated, we don't have to configure a lot of IP version 6 because that's automated with the network adapter that we have. That's already programming, which is kind of nice. And then your site local, you would see that it's FEC0. And then your link local cast, so whenever you see FE80, that's usually a link local. Okay? Okay. So before we do the calculation, we talked about base 10 in the last session. That's your counting number, 0 through 9, 10, we repeat, right? So 0 through 9 in decimal is equivalent to hexadecimal. So if I have a 0 in decimal, it's equivalent to a 0 in the hexadecimal. If I have a 7 in a decimal, it's equivalent to a 7 in a hexadecimal. But if I have a 10 in a decimal, that's equivalent to an A in a hexadecimal. If I have a 13 in a decimal, that's equivalent to a D. So it goes 10 is A, 11 is B, 12 is C, 13 is D, etc. And then it stops at 15 for decimal and F in hexadecimal. And that's the whole system, 0 through 9, A through F. And you can use a calculator to convert this, or you can use the chart that we did. So let's do the practice together. Okay. We are going to take this by chunk from left to right. Okay. I'm going to convert this with you in from decimal to binary and binary to hex. So a 4-digit binary, which we call a nibble, that's a 4-bit, is equivalent to 1 hex digit. Okay, so if I'm looking at a 2, you notice a 2 is made up of 4 binary digits. So 4 binary digit is equivalent to 1 hex digit, right? That means that if I have 8 bits, it's going to give me how many hex digits? 2, right? Okay. So let's start with the 2 on the left. Okay. So when I do the 2, I know that a 2 in hex is equivalent to a 2 in decimal. It's the same. So I just need to convert that to binary. So we're going to start with the scale decimal equivalent that we did in the past. And I only need 4 bits. I don't need to go above 8. Okay. So 1, 2, 4, 8. So it's not going to be a 1 because the 2 is not a 1. We put a 0 there. A 2 is a 2, so you put a 1 there. And it's not a 4, it's less than a 4 or 8, right? I can't subtract it. So basically I go down the scale and I want to see what I can subtract. I cannot subtract the 8, so put a 0. I cannot subtract a 4, put a 0. I can subtract a 2, put a 1. 2 minus 2 is 0. I don't have anything left, so I cannot subtract a 1, put a 0. So my binary is this. 0, 0, 1, 0.
How are you doing the math to get the binary? You do it again?
Yeah, so I take the 2, and this scale is always the same. 1, 2, 4, 8. I look at this scale and I say, what can I subtract 1, 2, 4, 8? How can I subtract 2 with an 8? No, it's too big. It's kind of like you have $2. You go down the aisle, right? Something costs $8. No, I cannot afford that. Put a 0. Something costs $4. You only have $2. No, I cannot afford that. Put a 0. Now you found an item that costs $2. Yes, I can buy that, right? I put a 1.
So in a sense, every byte is equivalent to
It's
one version 4, pretty much. You'll end up with 4
Yeah.
CIS. So the first byte will be
every byte is 2 hex digit, right? So the value here is equivalent to how many bytes?
gonna be
2 bytes.
2 bytes, yeah.
Yeah, which is 16-bit. Yeah, 4 plus 4 plus 4 plus 4 is 16.
Mhm.
Yeah, so I just simply do a subtraction method when I'm going from decimal or hexadecimal to binary, right? Only with the numerical value. Okay, let's try the next one. I have the same scale because it's multiple of 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. I only need 4 digits, right? So I need to make a 6 into a binary. So I go down the list. 6 cannot subtract 8. I only have $6. I cannot afford something that's 8. Put a 0. 6, can I subtract 4 from it? Yes, right? Something $4 and I have $6. So 6 subtract 4. Yes. So 6 minus 4 gives me 2, right? 2 left. So take 2 minus 2, I get a 1. So it's like 2 plus 4 is 6. So you have a 1 and a 1 here. And that leaves me nothing. So I cannot afford anything that's $1. Put 0. We established this last week as well, right? We did the conversion with subtraction. All right, let's try the 0. 0 is easy. Nothing, right? I have no money, so I cannot buy anything that's worth 1, 2, 4, or $8. So put zeros.
Still not understanding.
Okay, let's look at the one that we did here. So let's say you have $6 in your pocket. You go down the aisles, and this aisles always, the item always costs the same. Multiple of 2, $1, $2, $4, and $8. It's always going to be that scale. You have $6 in your pocket. Can you afford something that's $8? No, right? I cannot subtract 8 from 6 without going into the negative, right? So put a 0. I go to the next number or the next item. It costs $4 and I have $6. 6, can I subtract 4 from it? Yes. When you can subtract, you put a 1. What's left? If I have $6 and I bought something that's $4, I have $2 left, right? So I still have to subtract. So $2 is remain. At this point, can I afford another item that's $2? Yes, because I have 2 left. 2, subtract 2. If you subtract it, you put a 1. I bought that, right? So If you do the math, 4 plus 2 is 6, right? So I was able to get to subtract 4 and I was able to subtract 2. I have nothing left, 0. Can I subtract 1 from 0? No, right? If you cannot subtract, you put a 0. So you just simply go down the list starting from left. If you can subtract it, put a 1. If you cannot subtract it, put a 0. The remainder from the subtraction, you have to keep subtracting until there's nothing left. Okay? And then I have $0 here, so I can't afford anything that's here. Everything is bigger, so put 0. I can't subtract any of that number. I have zilch, nothing. Okay. And then let's look at number 3. 3, it's smaller than 8. I cannot subtract, put a 0. 3, smaller than 4. I cannot subtract, put a 0. Right? 3, can I subtract 2? Yes, right? Put a 1. So 3 minus 2, I have 1 left. 1, can I subtract 1? Yes, right? 1 plus 2 is 3. So it's on at that bit and it's on at this bit. So my binary is 0, 0, 0, 1, 1 for the 3. Any question?
Translate the whole thing, right?
Yep. And of course you can use the calculator to check this, right? Open up your calculator. Go to click this and then select programmer. So these are hex values, right? And I want to make it into binary. So you select hex and you punch in the value 8, 1, 2, 3, right? I'm doing the yellow now. And then I put that into bin and there I have my binary. Yes, you can use a calculator to do this, but if you want practice, you can do this manually. Okay, so for the next one, we're gonna do FA40. Okay. So I put a note here that an A is equal to 10 in decimal. Okay, so if we do FA40, an F is 15. How is that? A hex is F. So look at the chart that I gave you in the notes. F is equivalent to 15 in decimal. And when you see F, all the bits are on, right? That's the end of hexadecimal scale. So 1, 1, 1, 1. And F is gonna be all ones. Your A is 10. That's equal to 2 plus 8. So this bit is on and this bit is on. And so 1, 0, 1, 0. A 4, 0, 1, 0, 0, right? You can do the subtraction or addition. You can look in your mind and say, look at the chart and think in your mind and say, what can I add to be equivalent to that value? But when you come across the letter, make sure that you know that A is 10, B is 11, C is 12, D is 13, and so on, right? When you get to F, that's 15. Any questions? So the same thing that I approach all the other numbers. You take 15 and you do the subtract. Can I subtract 8? Can I subtract 4? Can I subtract 2? Can I subtract 1? So 15, I can subtract 8. That's 1, right? That left me with 7. 7 subtract 4. That's left with 3. 3 subtract 2. That's left with 1. 1 subtract 1. That's left me with 0. So all the bits are on 1, 1, 1, 1. And same thing with A, right? I go through the A, I take 10, subtract 8. I'm left with 2. I skip the 4. 2 subtract 2 is going to be 1. 2 subtract 2 is 0. I'm sorry. So put that 1 under 2, and then 0 subtract 1 is no, right? 0. So the reason why I have you do this, so you can see what the computer sees. When you have that address configured, this is what the computer sees. And it's important to see that it is a nibble for each hex character, right? Like if I'm looking at an F, that's 4 bits. An A, that's another 4 bits. A 4, that's another 4 bits. And then we can continue. So the answer, right? You can see my colorful things there. So what I want you to do is the first step is to chunk it up, right? So you try to do it 1 digit at a time, and then you have your binary value, and then you just add on to it to get your larger answer. Okay. I write it with 4 bits so it doesn't confuse me, and it's okay to do it that way. You don't have to all lump them up together, because after you type 0 and 1 so many times, sometimes that can get all mixed up. So I normally chunk it up to 4 bits, 4 bits, 4 bits, and 4 bits. And then after that, I go to the next section, 800, and then this section. So you do 1 digit at a time, right? F is 15, A is 10, 4, 0. And then here's A00. So if you already found the answer for the first A, that should be easy. 10, 10, 10, 10. The rest is 0, 0, 0, 0, 0, 0, 0. And then you can convert each of these. Or if you want to use the calculator, you can plug that in to check your answer. Okay. If you plug in the whole entire thing, it's going to spit out a very long. It might try to condense it with the E notations. So try to plug it in chunks at a time. Okay. All right, let's go in reverse now. Okay. So we established that each hex digit is 4 bit, right? And I color code this for you, so it's easy for you to see which is which. So we'll start with the flat 4 bit. Okay. 1, 1, 1, 1. If all the bits are on, we're gonna take 8. The scale is the same, right? Plus the 4, plus the 2, plus the 1 is gonna give us 15, which is equal to F. Right? I'm gonna take 8 plus 4 plus 2 plus 1 because all of those bits are on. So we would only add the decimal equivalent value that has the ones, that has the bits that are ones. Okay. So do you see that? Do you need help with that? Any questions? So earlier when I go in reverse, when I went from hexadecimal to binary, I subtract, right? Now I'm going from binary to hex, I add. Okay. So let me write out the first one in case you get confused. Okay. So let's do so my scale stays the same because it's multiple of 2. Why? Because it's binary. Okay, I'm going to clear this out and I'm going to do F for you, right? We did that earlier when we subtract. So I have 1, 1, 1, 1. You put the 1 underneath the scale, right? 1 here, plug it here, take the next one, plug it underneath the 4, take the next one, put it under 2, take the next one, put it under the 1. Right? So I know that all of these bits are on. That means I have to add the decimal equivalent of whichever bits are on. So the first one, it's on at the first one here. So I take 1, I add it. The next one, it's also on because there's the 1 there, right? I take the 2, I add it. And then the next bit is 4. It's also on, so I take the decimal equivalent, I add it. And then the next bit, it's on at 8. I have to add that one too. So if all the bits are on, then it's equal to 15 decimal, which is equal to F in hexadecimal. So that takes care of the yellow one, this first one. Let's do the next one together. I have 1, 1, 0, 1, right? Let me copy and paste this. And I'm only going to do 2 for you guys. You can practice the rest. So you clear out the bottom. And then I'm going to plug in the binary values, starting with the left. 1, 0. I'm sorry, this is the 1. 1, 1, 0, 1. Right? So the first, I see that it's on here, so that means I'm going to take the 8 and add it. I add the 8. The next bit is on here, so that means I'm going to take the 4 and add it. And then it's off at 2, so I skip that one. And it's on at the first bit or the least significant bit. So I add that one. So 8 plus 4 plus 1 is going to give you 13 in decimal, which is a D as in David in hexadecimal. Okay, so whichever bit is on, look at the decimal equivalent and add it. That's what you do. Just place it under the scale and then you can find and add it. Is that okay? Okay, then you can do the next one, which should be 9, and the last 4 bits should be B as in boy. So it's FD9B. And then you guys can practice with B and C, right? I did start with the 10B. Same process, right? Take the A, or take the binary and plug that into your scale, and then add the bits that are on. So that one is an 8. And then this one, 1, 2, 4. So that should be a 6. That should be a 10. That should be a 3. So once you get used to this, you can quickly look at the binary. You're like, oh, that's a 3. That's a 4. That's an 8, right? Should be quick. This and subnetting is the most math that we will do in this class. But you need to know computer math, which is number system like this. And, you know, we're not doing arithmetic or anything with it. We're just doing conversion, so. Okay, any question? Okay, let's look at octal. So I have all of that explained in the notes. Go back and look at the notes. Practice. Okay. Octal numbers are, you know, so when we had the 8-bit system, octal was popular. Octal is on the legacy system, but, you know, in case you need to use it for different things. So octal, the value is going to be range from 0 to 7. It's 3 bits. So hexadecimal is 4-bit long, right? Per digit. Octal, each digit is 3 bits, which is 0 through 7, because the next bit is going to be 8, right? So if you're looking at the scale, it is still multiple of 2, 1, 2, 4. It stops at 4. We don't go to the 8, right? Because that becomes a hexadecimal scale. So there's only 3 bits. Bit 1, bit 2, bit 3. Okay? So what you do is you just take the value and you subtract, just like what you did before with hexadecimal. When you're going from octal to binary, subtract. When you go from binary to octal, you add. Simple. Just like what we've done with hexadecimal, but it is 1 bit less. 0 through 7 only. There's no letters. There's just 0 through 7. Okay. And in the notation for octal, you see that it's the little subscript, it's 8. That means that that's the system that we're using, right? That's octal. Let's do the next one. Okay, so we are given an octal value 2, 4, right? We don't say 24 because that's a decimal, right? 2, 4 octal. And we want to convert this into binary. First, you have the same scale, 1, 2, 4, right? 3 bits. You're going to go down the list and you ask yourself, if I have a 2, what can I subtract? I cannot subtract a 4. I cannot, can I subtract a 2? Yes. So put a 1. So let me clear this out. This is confusing to some of you because you're like, what is that? What are you talking about? Okay, so take the 2, the first digit, go down the scale. Can I subtract a 4? No. Put a 0. A 2, can I subtract a 2? Yes. Put a 1. A 2, subtract a 2, I have nothing left, 0 left, right? So 0, subtract a 1, no, that cannot be done. Put a 0. So, okay. And I repeat with the 4. Clear this out. 4, can I subtract a 4? Yes, put a 1. Let me change the highlight color. Let's make it green. 4 subtract a 4, right? I'm on my second digit for octal now. Nothing left, right? I already subtracted everything. 0 out the rest. So I have 1, 0, 0. Same method, right? Piece of cake. Okay, so the answer is going to be 0, 1, 0, which is for the 2, and then 1, 0, 0, which is for the 4. Let's move this down. And then you guys can try the rest. I put some value there, but you can check my answer. So if it helps, copy and paste the table and then you can fill that out as you go. That helps me. I'm a very visual learner, so I have to have charts and graphs and things like that. That helps me. Okay. I'm going to cover 12 now because. So practice. For number 12, we're going to go in reverse. We're going to take the binary and we're going to convert it to octal. Same process that we've done in hexadecimal. We'll start with the first 3-digit. Sorry with the crazy highlight. Okay, so we'll start with 1, 0, 0. We just did one like this, but you can plug in 1, 0, 0. Right? I'm doing the pink now. 1, 0, 0. So the 1 is on at 4. So that's a 4. The rest are 0, right? I don't like the pink. It's hard to see. So the 1 is on at 4, so that's a 4. And then I move to the next 3 binary bits. I plug that in. Take out that. Let me put no color. All right. So we're going to plug in 1. I'm doing the green now, right? 0, 1. Let's look at the green now. So it's on at 4 and it's on at 1. So 4 plus 1 is 5. Okay. You see that? This is 5 because it's on at 1 and it's on at 4, so 5. And then the last one, it's on at 1, so it's a 1. So your answer is 4, 5, 1 is equivalent to the question A. Okay, you can try B and C. I think I started B. So plug in the binary and then the ones that are on, just add them together. So for the first 3-digit here, 0, 1, 0 for the binary, it's on at 2, so that's a 2. This should be a 7. This should be a 6. And then you can try the C. So make sure we know binary conversions to these number system because you're going to need it for some part of subnet down the line. Okay. We won't do it next week, right? It will be a few weeks from now, but That gives you a chance to practice. But once you get a hang of it, it's a lot easier because it's just multiple of 2 and you know which bits is on. You just visualize it and add them. Okay. Let's do 13 now. Any question? So, you can visit the link. And this link gives you some details about version 6, right? Remember we talked about hexadecimal is 4 bits. That's a nibble. We just went over that with the conversion so you can see that, right? We also converted something similar to this. And then on the next section, it talks about shortening. So there are rules in how we write IP version 6 addresses. Anytime that you have a bunch of zeros like this, you just omit them, you shorten them, right? Concatenate it into something like with a double colon. So whenever that you see a double colon, that just indicates that there are some zeros in between, right? These digits and these digits. Okay? This section of the address and this section of the address. Why write out a bunch of 0 when we can use a notation to indicate that? That saves us time.
Like the same concept of scientific notation.
Yes. Right, like the E for exponent, yeah? So it's just a way for the system to quickly, because remember that when you have values like that, that takes up storage, right? So we can concatenate it or condense it so that way it is easier. Okay, so that's rule number 1. Omit the groups of all zeros. We see that with the double colon. And then what if you have a bunch of zeros in the front? The leading zeros. Like this one, or this one, or those, right? Okay. So what you can do is you can also reduce them down so that way it would just be represented with just 1 0. Okay, like this. So when you combine the both rules together, in some cases you have addresses like that. You have this stays the same, right? You get rid of the 0 in the front. You only put the D following that. The F, the 0 stays the same. That's from the original address. You get rid of the 2 leading 0, you put F2. And so this is why when you're looking at shortened addresses, when it has less digit in between like this, just means that there were 0 in the front before. There were leading zeros. And we omit the 0 in the back right here, and we just put F10. And then we concatenate in between all these zeros with the double colon, right? So our address space is still going to be the same. It's just the way that we write it is shortened. Okay? Is that okay? All right, let's look at our question. Right, you have 2026. Okay? We're going to get rid of the leading 0 after the 6. So we don't put that on the shortened address. So you're going to keep CB0. So you bring that down. And then we're going to concatenate these guys with the double colon. We're going to drop the 0 in front of the F. So we're going to keep FC0. We're going to bring those digits down. And then these zeros right here, we'll just leave them as 0. Why can't I put a double colon there again? No, you can only use it once in the address. So we use it in the front, so we're gonna keep the ones in the back with just the 0. And then we drop the leading 0 in front of the A, we keep the A to E. Does that make sense? So anytime that you see a leading 0, you just drop it. Anytime that you see the 0 in between, you can concatenate with the double colon. But what if you already use it? You just shorten it with just 1 0 instead of keeping all 4, because it's 4 bits. So this is one way to write it, right? If I don't use it in the front, I can use it in the back. So I can have 2026, 2026, and then I drop the 0 in the front. So CB0 stays the same, and I keep these guys at 0 here, and then these guys at 0 here. And then I drop the 0 in front of the F, so FC0, and I concatenate these zeros right here with a double colon, and then I drop the 0 in front of the A, so I kept A to E. So whichever way, it's still the same address. It's just shortened. One we use it with the front 0 for the double colon. The other one we use it with the back 0 with the double colon. But you can't use it in both. Make sure we know this for the quiz and final exam. Any questions? Okay. You can come back to the link, and then it talks about prefix. So we can go to the lesson here. And then if you go down further, it gives you explanations for the prefix. So how many IPv6 addresses are available with the prefix? When you see a /4, it indicates 4 bits. And 4 bits, so we would start with 128 bits is the original IPv6 address space. We know that, right? At the beginning of the lesson, it tells us that your IPv6 is 128 bit. You take that and you subtract the /4, the 4 bits, which gives you 124 bits for the host. You're going to use this value as an exponent. So we're going to take 2, raise it to 124. So if you have a /6 there, you're going to take 128 minus 6, which gives you 122. And then you take 2 raised to the power of 122. So when you see the cider like this, I shouldn't say cider, it's for version 4. A /4, a prefix like this, you take that, you subtract it from the original address space, which is always 128. The difference, what's left is 124. That becomes the exponent of your base 2. So 2 raised it to 124. So if you see /16, right, you take 128 minus 16, which gives you the difference, and then that difference becomes the exponent of the base 2. All right, B, we take /24 here. So we take 128 minus 24, which leaves us 104, which is your nth value. And then if you do 2 to the n power, that gives you 2 to the 104. You can leave your answer like this, but if you want to write that out, you can. So that gives you the number of addresses that you can have with this prefix or that prefix, right? This is the number of addresses that you can have with /24, which is less. So as you notice, when you increase the prefix value, right, your address, the number of addresses that you have is less, right? So higher that value, less addresses. indirect relationship. Then for C, you take slash 60, so 64, you take 128 minus 64, which leave you 64, and it's 2 to the power of 64, is the number of IP version 6 addresses you have. So in subnetting for IP version 6, a lot of the time we indicate it by the prefix number like this to represent the number of addresses that we need on a certain subnetwork, right? Or segment, by using the prefix, the slash and the number. Unlike version 4, we'll come back to version 4 subnetting. And subnetting really is a way for us to use the addresses for the number of systems that we need by changing up the subnet mask. Do you have any questions for me? So whenever you see a prefix, what do we do for version 6? We take 128, subtract it, the difference. We're going to use that as an exponent to a base 2. Okay? Hard, not hard. Oh, compared to other stuff in computing, this is not bad. You know, I was reading steganography the other day, and because I'm redesigning my project for my forensic class. I'm gonna do a CFT forensic thing for them. Like they have to gain points as they accomplish the task. So you know, all of this play into binary conversion. So when you're hiding data, you simply manipulating a bit, usually the least significant bit. So if it's like 1001, you can convert the 1 into a 0, and it's a way that you can manipulate. You know, you can hide things that way. So you simply change it up. And then there are applications that does that for you, but you know, manually that's what's happening in the back. Any question? Okay, let's do 15 or answer 15. It says, how does a computer system generate its own IP version 6 without using the same address of another system in the network? How does it know that, right? We know that each system has to have a unique address or we're going to have a conflict. Because how is it going to send things appropriately? Well, there's an auto configuration process, and this allows it to check what addresses already been in use on the network by soliciting the neighbor. So before that, it picks up an address or gives itself an address, what it does is it's looking at all the systems that are connected around it. That's called neighbor solicitation. And it sends the neighbor the information. It's kind of like you're living in the neighborhood and you ask your neighbors, right? What's your home address? What's your home address? What's your home address? And then you figure out my address is not going to be like that, right? Schematically, it has to be in the same scheme, but not. It has to be unique. So in that process, it's able to see what's already been in use. And then if the other system is using that address already, it's going to say it's already in use. You cannot take it. It's kind of like you ask your neighbor, can I use your home address? And they say no. Right? This home address has already been taken. So that means that the other address, you have to have an alternate address, a different address, a unique address. Okay. So this is how the auto configuration work is to do neighbor solicitation, and that allows the system to come up with a unique version 4 address, which is so much better than what we've done with version 4. We rely on the human configuration, or we would need the DHCP scope to be able to generate that IP address or assign the IP address for that system. Now, when you're working with IGMP, right, a lot of these protocols are now adapted for version 6. So when you're doing routing and switching, you would see that certain protocol, it would say V6, right? DHCP V6, that's able to assign version 6 IP address. The original DHCP is for version 4. So we have adapted some of the protocol for the newer IP address scheme. And similarly, you would see the same thing with IGMP. But instead of having, like if we using Clean, ICMP version 6, IGMP, in the older version, you just use MLD, which is your multi-class listener discovery. So this is the way that we can send to a group of IP version 4 systems, right? But version 6 has adapted most of your common network protocols like ICMP version 6, and then you would see like DHCP version 6. So you're able to set up, right, a server that would assign only version 6 IP address. Like how we did with version 4, but adapted for the newer address. Any question? So as you take, this was not prevalent in the older version of the certification. I know that Network Plus fully transitioned to the newer version now since, we've passed July. July was the cutoff for 006. We now integrated 007 certification. So as you move to newer version of the certification, you would see more prevalent questions that would be related to version 6 IP addresses. Okay. So the prefix that we talked about, right? The CIDR, that's classless interdomain routing. You've seen this also in version 4 with the slash. So when we do subnetting with version 4, you would become very familiar with it. But we already know how to do the math for that, right? We did that with the example. Okay, so the version 6 protocol, like what I talked about, IP, ICMP, MLD, which is for the older version of IP. And then you have ICMP version 6. The neighbor discovery, this is very popular with the routing systems. So your ND, DHCP6. And then routing advertisement, it uses also ICMP version 6 for stateless. Okay, so with the tunnel protocols, when we're looking at things like IPsec, things that would establish a tunnel so that way it would protect the communication, the traffic that cross between the systems using encapsulation. So when we transition to version 6, we have to have the proper protocol and technology to adapt for it. So 624 is a common tunnel protocol. It encapsulates version 6 packets. You also have Torito, which uses network address translation on the NAT devices. So you do see some of this with communication system, routing systems, right? And then there are other protocols here, ISATAP. This is automatic, and then Morito, which is going to be the Torito client side for Linux systems. So it's specific, it works together with this one. So when you see these, right, when you configure network appliances, you might run across these for tunneling purposes. And then 426 is in reverse. So to answer that question, we can come back to that section of our notes. Right, 17 IP version 6 tunnel protocols that's used by routers to determine the endpoints. 624, Morito and Torito. And then for 18, we need to identify the services. So I'm saying so protocols is used for services, right? Like HTTP for web services. Okay, so we need to look at the type of protocol and services that we have. So the first one, for 18, share files and printer between Windows and Unix systems. And this will be important for some of you who configure. Like you might have a mixed environment where you have Linux machine, like server, and then you have some Windows client. And in order to print, right, you have to use a service called Sandbox. You have to initialize the service or install the service. Otherwise, it will not work. We want to resolve computer names like host names to an IP address. We would use wins. Back in the day, NetBIOS only uses names. So let's say that I would say server 12345 to the IP address 10.0.0.x 111, right? That's gonna be wins. Now wins come default in the installation of DNS, but you don't have to allow it, right? It does come in the back, and with wins you have flaws. So you need to assess the vulnerability behind it. And then when we need to translate public to private addresses and private to public addresses, we use network address translation, NAT. Your router does this at home for you. Okay. And then your virtual machine has this configuration on, so it takes the virtual machine IP address, convert it to the regular LAN address that you're sitting on, and then send that out. And that's how you're able to get internet. Today, when we switch to host only, so we don't broadcast address to the rest of the network, right? We disable the NAT option on it. So it doesn't use the physical network addresses and convert it with our virtual machine. D, plan, document, and manage all IP subnets. We use IPAM. E, remotely connect to Windows networks to access files and applications. Remote desktop protocol, your RDP. Whenever you see remote in Windows, that's RDP. I think we touched on port numbers and stuff in the past. And then F, minimize configuration of clients by broadcast services on the network to the clients. It's called zero config. So it sends the services to all the clients on the network. Is that ideal? Probably not. Probably use up a little bandwidth at the same time. Question. Okay. So make sure that we go through, right? Understand, read through, be familiar with the terminology, the protocols, the associated services, because doing an assignment one time won't help you remember. If you're studying for certification, you have to repeatedly, right, go through and try to memorize them. The list is a lot longer than my assignments questions. I just summarize some of them. So make sure that you go through like NFS, stuff like that, SMB. And for security people, know your protocol. I can't emphasize that enough, right? Like if you become a first incident response person and things come up on your report and you don't know what that is, right? That doesn't help you understand the vulnerability behind it. So know your protocols. Okay, let's take a break. I'm gonna stop recording. When we come back, we'll do the lab. And then